Start with the numbers. The universe is approximately 13.8 billion years old, with 100 plus billion galaxies, each packing billions of stars and, likely, even more planets. If even a tiny fraction hosts life, and a tiny fraction of that life becomes technological, the galaxy should be lousy with radio chatter, probes, or at least one neon alien billboard. The Drake equation, while more conversation starter than calculator, often suggests non-zero neighbors. Yet we hear nothing. No unambiguous signals, no Dyson sphere-level renovations, no politely parked saucers. Possible resolutions compete. Number 1, life is rare. Abiogenesis is a cosmic fluke. Number 2, intelligence self-sabotages, the great filter, either behind us or ominously ahead. Number 3, they're quiet by choice, zoo or dark forest behaviors. Number 4, we're listening wrong, brief, narrow, or non-radio windows. And number 5, space-time is huge and slow, signals fade, travel is hard, patience is not our species' core skill. Also, techno-signatures might be transient. Civilizations may use spread spectrum, narrow beams, or non-electromagnetic channels like neutrinos or gravitational waves, which make our radio ears hilariously obsolete. Either we're early, unlucky, or not looking with the right ears. Cute, the cosmos left us on red. Ready for a night sky paradox that flips the brightness to max? Assume an infinite, eternal, static universe with stars spread everywhere. Then every line of sight should land on a stellar surface, stacking light until the whole sky blazes like the sun. It doesn't. The fix requires dropping those old assumptions. The universe isn't eternal or static. It's finite in age and expanding. Because light travels at a finite speed, only photons that have had time to reach us can contribute. Vast regions are still en route. Meanwhile, expansion redshifts distant starlight into infrared and microwaves, dimming what we see. Dust can't save the old idea either. Absorbers heat up and re-radiate. You still end up bright eventually. Add the reality that stars are mortal, clumpy, and far apart, and you get a sky that's mostly black, with a whisper of leftovers. The cosmic microwave background, visible only to instruments, not your eyeballs. And because star formation had a beginning and will have an end, there simply aren't infinite light bulbs burning forever to fill every pixel of sky. Darkness explained. Speaking of things we can't quite see, what happens to information when gravity turns the dial to absurd? Quantum mechanics demands that information is never destroyed. General relativity says a black hole swallows anything that crosses the event horizon. Stephen Hawking added a twist. Black holes radiate thermally and can evaporate. Thermal radiation carries no details, so when a black hole vanishes, where did the info go? If it's truly lost, quantum theory snaps. If it's not, relativity gets testy. Proposed doubts: 1. Information is encoded in subtle correlations of Hawking radiation, not visible in a simple thermal spectrum. 2. Holography. What falls in gets stored on the horizon's surface description. 3. Soft hair or horizon microstructure that tags outgoing radiation. 4. Quantum gravity effects. Islands, page curves, implying that, globally, the radiation does carry the details back out. The page time marks when the radiation's entropy peaks and starts revealing clues. Before that, it's just noise. Afterward, the universe slowly leaks the spoiler-filled director's cut. No single picture wins all arguments yet, but the modern vibe is, black holes are messy accountants, not arsonists. If black holes keep the books, can humans at least keep time straight? Let's ask a pair of very confused twins. Two identical twins, one stays on Earth, the other rockets off near light speed, flips around, returns. Special relativity says moving clocks tick slower. Each twin sees the other's clock lag. So who ends up younger? The symmetry breaks when the traveler turns around. Acceleration switches frames, and that non-inertial detour is the key. Example: fly 10 light years out and back at 99% the speed of light. Earth measures roughly 20 plus years round trip. The traveler's time is compressed by the Lorentz factor, gamma approximately 7. Only a few years pass on their wristwatch. We've tested the principle at humbler speeds, atomic clocks on planes, fast-moving muons, and everyday GPS corrections. All agree time dilation is real, not sci-fi garnish. Bonus twist, relativity adds gravitational time dilation. Clocks deeper in gravity wells tick slower, so the twin who skimmed near massive objects could come home younger, which is a weird flex. Congratulations, you've time traveled to an awkward birthday party. But will the party end because the universe eventually runs out of useful energy? If the universe had existed forever, the relentless creep of entropy should have flattened everything long ago into a lukewarm, do-nothing fog. Maximum disorder, zero free energy, no cosmic drama. Yet we see stars, galaxies, coffee, you. The resolution: the universe has a finite age and began in a low entropy state, so it hasn't had infinite time to smooth everything out. Expansion complicates and delays the endgame by creating more space for entropy to grow into. Gravity also plays a sneaky role. It can locally decrease entropy by clumping matter into stars and galaxies, even as total entropy, especially in black holes which have colossal entropy, soars. Long-term forecasts are bleak. Stars fade, black holes evaporate, particles decay, but that's on timescales that make forever look punctual. Right now, stars are giant free energy vending machines powered by temperature differences. Once those gradients disappear, chemistry, biology, and drama sputter out into eternal, whisper-quiet, thermodynamic boredom. We're not cold yet. Before the heater dies, though, time travel tries to write its own origin story. Enter a loop with no first chapter. Send an object, idea, or set of plans back in time. It becomes the very source of itself, a closed loop with no beginning. Hand Shakespeare a copy of Hamlet, he publishes it, you later find that edition and take it back to him. Who wrote it? Causality shrugs. Physics doesn't forbid closed time-like curves in certain solutions of Einstein's equations, but whether nature actually permits them is another matter. The Novikov self-consistency principle says, if time travel happens, only self-consistent histories occur. No grandfather paradoxes, just tidy loops with questionable originality credits. It's logically tight, but philosophically spicy. Free will looks pre-scheduled and information appears unearned. Paradoxes vanish if the loop is the only self-consistent option. You can deliver Beethoven his symphonies, but you'll never find a version where he writes dubstep instead. If the cosmos allows copy-paste causality, what kept the early universe so eerily uniform everywhere? Time to look beyond our horizon, literally. The cosmic microwave background, CMB, is astonishingly smooth, temperature differences of about 1 part in 100,000 across opposite sides of the sky. Yet those regions are so far apart that, in a simple Big Bang model without extras, there wasn't enough time since the beginning for light or heat to travel between them and even things out. Cosmic inflation is the patch and upgrade. In a split second after the Big Bang, space expanded exponentially, stretching a small, causally connected patch into our entire observable universe. That early patch could equalize, then inflation pulled it far beyond mutual contact, leaving behind uniformity plus tiny quantum ripples that later grew into galaxies. Bonus benefits: inflation explains why space is nearly flat and why structures look the way they do. Those quantum jitters stretched to cosmic scales, seeded over and under densities we now map as acoustic peaks in the CMB power spectrum. Yes, the universe has a favorite playlist. Uniformity checked. But if the cosmos can inflate, could it also randomly cough out fully formed observers? Please welcome the creepiest guest star in cosmology. Start with Boltzmann's idea. In a very large or very old system, rare low-entropy fluctuations can happen. Our orderly universe could be one such fluctuation from a higher entropy background. Trouble is, if the cosmos lasts long enough, it's far more probable to fluctuate a single self-aware brain with hallucinated memories than to assemble an entire low-entropy universe like ours. If that's the typical outcome, most observers should be isolated Boltzmann brains, which would make our trust in observations awkward. The usual escape routes insist that acceptable cosmologies suppress Boltzmann brain dominance. The universe doesn't last forever. Inflationary scenarios decay fast enough. Or the measure we use to count observers penalizes these freak events. Also, real brains need messy histories. Evolution, fossils, microwaves in the sky, whereas a pop-up brain gets none. Our data-rich universe screams long story, not 5-second improv sketch. And with that dizzying roll call, our paradox parade reaches the gift shop. Receipts are non-refundable, unlike information in a well-behaved universe. If your brain survived this paradox speed run, reward it with 3 clicks. Like, comment your favorite mindbender, and subscribe to CosmoBinge. Because nothing says defy entropy like feeding the algorithm a dose of fresh cosmic confusion.